This video is on Swift and Swift-T, presented by Adam Ordway,
Ben Johnson,
and Brandon Sloan.
Now, what exactly is Swift? Although the name Swift suggests that it's Apple's programming language, the Swift that we are referring to is a fast and simple scripting language with the intent of parallel programming. Swift is a scripting language which is built from Java, but uses syntax that is similar to C and C++. Swift also shares common features with other programming languages, such as loops and conditional statements and built-in arrays.
Since Swift is a naturally concurrent language, whenever all variables used as parameters of a function are defined, the function will be executed. For example, when y equals f of x is calculated, immediately following z1 and z2 will both be executed at the same time or concurrently, as long as neither gy of 1 or gy of 2 alters the initial value of y. When a Swift program is executed, it will display incremental updates to show the progress of your program, as shown in the figure below. You can create a swift.config file, which will allow the user to define different remote resources to run tasks off-site. Another benefit of Swift is that since it is based on Java, it is extremely portable and can be downloaded to any machine you might use.
Swift is designed to compute large amounts of data over many processes that can be run multiple different ways, whether that be several processes on one machine or across an array of machines. To demonstrate this, we can use a basic example. Here we have a basic program called multdiv.cpp that takes numbers on input and runs a few operations in order to simulate data operations. As input, there are 200 different files with 1 million numbers each, simulating the separation of a large set of data. To execute the operations, we have two programs to show linear and parallel operations. The linear program is a shell script that runs multdiv 200 times for each input file, showing the linear processing of data. The parallel program is a Swift script file that runs the program in parallel using as much of the computer's processing as it can. The main advantage shown here is the ability to write a parallel code in a serial fashion without worrying about how to structure complex processing. Swift automatically parallelizes when possible, only serializing data when it must. In the case of the example below, the data is separate and has no need for serialization. As you can see here, the linear CPU chart shows it is using only one core, and the linear progression takes almost 18 minutes. On the other hand, the simple Swift code running the same commands uses at least 2 cores at a time. This extra processing takes nearly 7 minutes off that time.
Swift-T is a newer version of the original Swift-K. Swift-T runs on a turbine engine, hence its name. While Swift is able to run across a large number of cores, it is limited to a single node. Due to its implementation, Swift-T is able to support a much larger number of tasks than Swift or the previous Swift-K. It also includes various other improvements, such as being able to execute scripts from popular scripting languages and run code from C, C++, and Fortran. Another key feature of Swift-T is that it is run as a single MPI job. Swift-T, unlike Swift, uses a turbine to distribute tasks using MPI to achieve this. According to the Swift website, swiftlang.org, the turbine combines the performance benefits of explicitly parallel asynchronous load balancing, an MPI library, with the programming productivity benefits of implicitly parallel data flow scripting. So what does this actually mean? This means that it helps reduce the bottlenecking that occurs using a single compute node, which is especially helpful when increasing the number of tasks requiring distribution. However, due to the overhead costs introduced by MPI, it does not benefit smaller data sets and is used primarily for programs such as large area power grids.
Special thanks to swift-lang.org, and that is Swift and Swift-T in 5 minutes.